his time, if we say distance 100 divided by 9.69, we are going to realize that it simply means his rate or his speed was at 10.3199 meters per second. So which means in every second, we are saying Usain Bolt has covered 10 meters, 0.3199 up until I don't know what other decimal is going to follow per second. That's the rate he was looking at. If we want to look at this at a big picture, we're going to change. Usually we look for time and distance for speed. We usually look at it in kilometers per hour. Let's change this into kilometers per hour. So per hour, what it means is, since he was traveling at this per second, so in an hour, how many seconds are there? In a minute, there are 60, and there are 60 of those minutes in an hour, which is 60 by 60. That's going to give us 3.600, which is 3600. So if we multiply 10.3199 by 3600, what do we get? 3715, 1.70 702. I guess that's one. That's these are meters per hour. Is that all? So which means if we want to convert this again from meters per hour to kilometers per hour, so I would need to change this into kilometers. And to change this into kilometers, remember in a kilometer there are 1,000 meters. So which means I'm going to divide this by 1,000. That's going to give me that it was going to be 1, 2, 3. It's going to be 37.15 approximately kilometers per hour. This is the speed that we are saying at average. Remember, this is average things we are dealing with. It's not yet the exact thing at the exact point. So now let's think. We want to go visual. If we are to be asked to draw a graph to represent his entire race from the beginning of the race to the entire of the race, we are going to have something like this, which is distance here and time here, and this time is in terms of seconds, and the distance is in terms of kilometer. So we are saying he has reached from 0, it was a 100-meter race, and the time he completed the 100-meter was 9.69, right? So which means here approximately, I think somewhere here, that's where he completed, and this is from 0 where he started. And if I'm to ask one of you guys to draw a graph to represent this, it's tempting, and you can find out that some don't want to draw a graph like this, a straight line graph, which is pretty wrong. From the video you watched, there are 2 reasons that can deny the idea of a straight line. What would be the reason? What would be the reason? At the beginning of the race, he didn't just start with his top speed from the beginning to the end. At first quarter, we see that he was a little bit slower because he was still amongst the other his competitors. So this graph could have started a little bit slow. And at the middle, the graph is better steep because we can see that he covered the bigger distance in the shortest time, because that's where he increased his speed until he became an outstanding, where we can see that he's now in front of everyone. And at the end of the session, at the end of the race, we can figure out that he was a little bit slower at the end of the race, because you realize that at the end of the race, he was a bit slower because you see he started celebrating at the end before the race has ended, which means if he had focused, like continue with his speed which he used in the second and third quarter, he would have reached less than 9.69 seconds. So this graph is just telling us that he started with the same speed from the beginning to the end, which is not true. So this graph cannot present or represent Usain Bolt's race for 2008. But this one could be a better one. Let's draw another one. Something like this. We realized that from the 0, which means at the beginning of the race, everyone was not going anyway. So the graph was like at 0. The distance was not going anyway after the gun is started. And then it goes a little bit up. And when it goes up in a slower mode, and then here, something like this. That's a little bit better. Right. This is the graph that can explain better. Now, if you look careful in both the graphs, there is something that we want to look careful. Let's go back to the one that is wrong, that we said it's a wrong graph. But if you look at this vertical distance, is the rise of the graph, right? And the time is the horizontal, which is the run. If I compare these two, the vertical distance, which is the vertical distance, which is the rise, and the horizontal distance, which is the time, if I divide these two, like rise over run, what will I get? That's what I mean. If you look there, is that correct? That's gradient. And if you look careful, so we are saying, if you say distance over time is speed. So which means when we were dealing with the speed here, actually what we are really doing it right now is gradient. Is that so? And if we are to look in the new graph with the green and yellow, if I'm to tell you to calculate gradient there, what will you do at your ordinary level information? How are you going to calculate gradient of a curve to draw a tangent? Let's say I said find the gradient at this point. What you would have done is to draw a tangent at that point. And then you find the gradient of the tangent. And that gradient of the tangent at that point, that will be the gradient of that point. Because the tangent is passing through that same gradient, that same point. Is that so? And then now, my next question is, someone would have drawn a tangent a little bit different from that. Something like this. And between the yellow tangent and the red tangent, everyone was going to get a different gradient at that particular point. So my question is, the yellow one or the red one, who is correct?
The red one was
if you look actually, even the yellow one, it touched once. Yes, it's lying on the graph because some parts of the graph they are following the straight. They are seem like straight, but it's not straight. Yes, but there's no problem with the tangent. So now the problem now, that was the problem of the gradients we were using at grade 11. They were not giving us the exact gradient. They were giving us an approximated gradient. So at this point now, do you realize that if I am to draw or if I am to shorten the red line and the yellow line, all of them, they were going to be one line at some point. If I shorten them up towards the point that I want gradient at, you are going to see that from their point of contact, if I shorten them all to be very small, they were going to do the same thing. Like those, all of them gradients, they were those two tangents, they are going to be one part. They are going to be one line, and all of them again, they are going to be something like same with the green line. It's like they are fitting in the green line if I shorten them enough, all of them. Which means if we are to look careful, if I'm to do something like this, let me do this quickly. If I'm to draw a rectangle, a triangle, I mean, between these 2 points, like this rectangle triangle, right? This distance is going to be the rise, and this distance is going to be the same run. Is that so? So if we look careful on this, we are going to realize that let's call this curve f of x because it's the function. Let's make it a function in terms of x. Is that so? And let's say the first part of the first corner of the triangle, let's call that distance x. And if I move a little bit until this point here, let's call that distance between, let me call it h, right? If I call that distance h, what it means is this point here is going to be x plus h. Is that making sense? So which means, remember the function notations. If you have something like y is equals to f of x, whatever you can put in for x is going to give you the output, which is the value of y. Is that making sense? For example, y is equals to x squared. If I say find f of 2, you are going to substitute this x by what? By 2. So y was going to be 4. So since my gradient, my function since my function is f of x, I'm going to say if I plug in this f of x, this x into f of x, so my y here is going to be f of x.